Good afternoon and welcome back to the water stream session for this afternoon session. Today I'd like to welcome Brent Williamson. He's our next presenter. Brent Williamson is the Western Canada Technical Sales Representative for Canada Pipe. He's been with the company for 6 years and specializes in education and presentations. Brent works with engineers and municipalities daily, helping to write specifications or offering creative solutions. So thank you, Brent. I'll open it up to you. Come on up here.
Hello. First, I wanted to say I walk around a lot, so stay focused. Thank you very much for the EOCP for inviting me back. I was here last year, so I really appreciate it. It's a really great opportunity to talk to operators, and this presentation is really involved. There's a lot on here. We're going to be switching focuses a couple of times during the presentation. I'll try to guide you through that. But this is a really great opportunity to see how we get the future actually comes from the past in a lot of ways, and we get our inspiration from the past, and we can get those solutions from the past too. So what I mean by that is you're going to see that sometimes new material isn't always what we need, and we can get solutions for environmental causes from the past. And what I mean by that is using ductile iron. And it comes from cast iron. So you're going to see what that means. So I'll hopefully be able to work all this properly here. There we go. So what's the difference? What are we talking about when we're talking about the difference? Well, the difference is cast iron is about 45 psi tensile strength, 21 psi yield, and there's no elongation in cast iron. So what does that mean? Well, it makes it a very strong product, but it also makes it a very brittle product. So it's not going to be able to flex and move, which is why ductile was invented. And ductile is 60,000 psi tensile strength, 42,000 psi yield, and a 10% elongation. So that really gives us a lot of flexibility when it comes to frost heaving, temperature changes, movement in the soil, and you're going to see all that in a bit. So that's what it means. It means flexible, and we can actually do that with ductile iron pipe and move it around. It's not as stiff as maybe you think it might be. So what are we doing when we're making ductile iron pipe? Well, technically, we're really just fancy recycling. And I'm going to show you a process for that. Here's what the process is. It all follows this path. And this is all going to be important later on in the presentation, where we talk about corrosion, where we talk about hydraulics, where we talk about seismic capabilities. All these things, we are adding energy into this raw material. We are energizing raw material. So we are recycling raw material, and you're going to actually see the process of it. I included a video, short one, and I wanted you to take a look at it. It's a great video that actually shows the process of recycling and making of ductile iron pipe. So if we can just press play on that, and you can see. Where all of Western Canada gets the pipe from. We recycle about 850,000 cars a year. So that's about a car and a half a minute every day. And that's only one ductile supplier. There are 3 ductile suppliers, and they probably do the same or more. So this is where we're adding the magnesium into the cupola, and that's changing the mechanical or the chemical structure into ductile. This is where they're putting it into the centrifugal casting machines. So there's it coming out, and we can pump out a pipe about every 3 minutes or so. Everything is a closed loop process when you're talking about ductile iron pipe. So we, all the sand cores that we use to make that they're hammering out there, that's all taken and recycled again and used again. The water is circulated back through the system and recycled again as well. This is where we're putting it into the annealing oven when we heat it up to about 1800 degrees, and it'll change its chemical structure and it'll become ductile iron pipe. This is the process right here where we're basically just beveling edges, which is done by hand. This is the testing facility. They will test a pipe every 15 minutes, and we'll test for metallurgic of the metal. We'll test for impact strength, tensile strength. It's tested to a very specific AWWA standard. And then after that testing, we will actually test it, and you'll see it in a second. We'll test it through the process of the hydro testing, where we'll put it up to about 500 psi. Every stick of pipe is tested to 500 psi before it leaves the facility. Now that's the hydrostatic test. And then it goes down to more testing, and we actually will look at all the pipe and we'll check the batch numbers. We will be testing all of the ovality. We will be testing thickness, which you can see right there. That's the internal diameters that they're testing in 3 different places. So it's very involved as far as what we do. This is the cement mortar lining facility. We're going to talk more about cement mortar lining when we talk about corrosion. It's a very important thing to do, and we can kind of move on, but that's basically what that is. So when I said before, it is 98% recycled material that goes into ductile iron pipe. Like I said, it's mostly cars, train cars, and it's actually 100% recyclable itself. So once the product is done its life, which is about 100 years, you can take that pipe and recycle it as well. What does that mean? What is the composition of the pipe, and what are we talking about when we're casting it? Well, there's a net thickness, and we add 2 to the safety factor of it. There is a service allowance, which is about 0.08 of an inch. Casting allowance, which varies between 0.5 and 0.9. And basically what that adds for us is safety factors when we're talking about pressure rating. So let's take, for example, the 300 PSI pressure class. We'll add 100 PSI allowance for surge, 2-to-1 safety factors, which means that pipe can actually handle about 800 PSI, which is pretty substantial. These are the available joints that we talk about when we're talking about ductile iron. We can do mechanical joints, flanged, push-on, and they all have their purposes. The one that's being touted as the next one, and one we're selling a lot in BC, for example, and also in other places in Canada, is the TR Flex. TR Flex is a restrained joint pipe, and it can be restrained without using external restraints. So we're talking about cutting down labor, we're talking about cutting down materials. It's about safe to about 800 PSI, the same as the other ones are. And this is a short video, 4-minute video of how we actually put it together. I don't even have to talk on this one. So we'll play that one and take a look and see how we actually do it.
Pipe in a casing, pipe bursting, or any other application where you have unstable soil. McWane Ductile manufactures TR Flex pipe in sizes 4 through 36-inch diameter. Okay, we've got a 20-inch pipe here. We're going to show you basically the breakdown of this, how this locking system works before we assemble it. So in essence, you've got a left-hand and right-hand lock that would go into the slot of the bell. When your pipe goes home, your left hand and right hand separate. You've got a rubber piece that keeps them separated. And then up here on this other side, we're going to show you how this works, is the bead on this spigot will engage the locks as such as shown here. These will be in the top slot of the bell. First, got to make sure that the gasket area is clean. So want to make sure this is all cleaned out. Want to get our gasket, want to loop it up top to assemble it, make it easier to go in. Put it in our groove. Okay, now that our gasket's in, we want to feel around, make sure that it's properly seated so that it won't get hung up when we push the joint home. The next thing we need to do is to lubricate the gasket. We use an NSF 61 approved lubricant. Only use lubricant provided by Ductile when you're assembling your joints. So you get all the way around and lubricate the gasket, face of the gasket. We also want to lubricate the adjoining spigot back to the weld bead. Now we're going to assemble our joint. We're going to use these locking segments to form one half of the ring in this slot, and we're going to use these locking segments to form the other half of the ring in this slot. First I'm going to do is insert the right hand lock. Next, I'm going to insert the left hand lock. Insert the rubber piece, the U-shaped form, to get the lock placed. First I go with the left hand lock into the slot, slide it down, insert my right hand lock, slide it up. Notice if I let go of that, gravity takes over, falls down, hold that back up in place, take my rubber piece, put it in a U shape, push it in to keep my lock separated. We now have a fully restrained joint. Now allow us to demonstrate.
Okay, so TR Flex pipe, they're showing it being pulled apart there by two forklifts. The actual amount of force that it would take to pull those two pipes apart would be two 747 jets pulling on either side. That's what it would take to pull that joint apart. So it's very, very durable and very, very safe, which is why we're using it now for seismic considerations, and you'll see that later on in the presentation. But here's some other things that TR Flex pipe can do. We can do, and ductile iron pipe can do. So we can do a pipe on supports. We can do river crossings, when this is going to get into your probably questions that you're going to have about corrosion, and you're thinking it's going into water, and it's happened to it, but water does not corrode iron pipe. So you're going to find that out in a bit. We can do bridge crossings, which is a very, very common application for TR Flex. Pipe in casings. We can also do horizontal directional drilling. Also one that they don't really think and equate to ductile iron pipe, but we can do that, and we use TR Flex for that. And we obviously the inside liners, we do cement mortar lining, which is the common one for water. We use bare pipes for steam and high temperatures, and we also use Protecto 401. And what I get a lot of questions is used for glass lining for sewer casings, which is this is what Protecto 401 looks like. But glass lining is actually more expensive, and it's not as durable as ceramic epoxy lining. So that's what the new application is. So we use it for, you know, surge pressures, high temperatures, and chemically resistant applications. So we're going to get into corrosion now, which is a lot of questions that you probably have about ductile iron pipe and why you should use it as opposed to other materials like PVC or HDPE, because they'll say, well, we can't use it because we have hot soils and it corrodes. Well, why do we cement line a pipe? You probably saw that in the manufacturing video, but why do we do that? Well, we do it for this reason here. We do it for internal corrosion, and that is a problem that used to happen before we used to cement line pipes, and we have cement line pipes now for 90 plus years. So it's been around a long time, but we do it because we have to create a physical barrier between the water and the pipe. So this is what it looks like when they're putting it in. And you can get it cement lined with the seal coat so it looks black, or you can get it without the seal coat, whatever you like. So when we're talking about corrosion, how do we know what we know? Well, how do you know what I'm telling you through? We get it from all these different studies. We get it from NACE, we get it from the American Petroleum Institute, American Society of Mechanical Engineers, National Standards Institute, and we also get it from another company called DIPRA, which is the Ductile Iron Pipe Research Association. And what they come up with is, what is corrosion? What is corrosion defined by? Well, corrosion is defined by the deteriorated by the environment. So anything corrodes, why it is and how that works. So here's an example of how DIPRA helps. This is the DIPRA test site, and they have them all over North America, including in Canada. They have tons of different specimens of pipe, and this is how they do it. They actually put the pipe in air, or it's covered, or it's cathodic protected, and we see how it reacts. Right now, currently, we have about 300 different soil environments and about almost 1,400 specimens that we know. And we know for a fact that ductile iron or iron will last in non-aggressive soils upwards of 370 years. And how do we know that? The first pipe that was ever installed was installed by Louis XIV in France, and it was a cast iron pipe, and it lasted until the 1980s. So that's how we know how long it will last. We'll get into corrosive soils after. These are the different types of corrosion that we talk about when we talk about iron or pipes in general. We talk about microbial corrosion and we talk about galvanic corrosion. And this is where we're going to get into a bit of science. So bear with me and I'll try to walk you through it. So microbial corrosion is a biocorrosion. It's caused by microorganisms. It's oxidation, and it's not actually rust. You need an electrical connection for corrosion to occur. What we do worry about is galvanic corrosion. Galvanic corrosion is where one metal corrodes preferentially for another when an electrical connection is present. It's in the presence of an electrolyte. What do I mean by that? Well, to get into that. So here's some tests for you. Now, when you think to yourself, you answer yourself when you're watching, is this corrosion? Is the Statue of Liberty corroded? And the answer is no, she's oxidized. And when she came from France to the Americans way back in the 1800s, she was bright and shiny copper. So what happened with this is it patinaed, and it turned, and what the copper did was it's protecting the rest of the steel structure underneath it, and that metal has lasted for hundreds of years now, over 100 years now. So that's what it did. It was actually shiny copper, and then it turned to that. So it's not corrosion, it's oxidization. What about this? Let's take a closer look. This is actually Corten steel, and that did the same thing. It'll put a barrier of oxidation on the steel to protect that metal. So that's not all the time when you see different things like brown on metal, is it rusting? That's not what's happening here. That's oxidation. It's actually protecting the metal underneath it. Here's an example of a pipe. This is in the city of Vancouver. Then they were putting in their large diameter pipe, and they left this above ground, and that is oxidation. It's actually protecting that metal underneath it. When it goes into the ground is where we have to worry about corrosion, and we're going to get into that. Again, it's discoloration, it's not rust. This is where corrosion is. So you can see this is what it was buried in hot soil without any protection. Here's an example again, and you can see on this one that it's following a path. And why is it following that path? There's a reason for it. You can see at the 12 o'clock and the 6 o'clock level, there is no corrosion. It's corroded at the 9 o'clock and the 3 o'clock. Why is that? So we're to try to figure that out. So we'll focus on galvanic corrosion, and galvanic corrosion is an electrical chemical process. Here are the susceptibility of metals. So what we talk about when we're talking about different metals, and different metals corrode different ways, right? So magnesium, zinc, aluminum, mild steel, cast iron, they're all on the lower end or mid end. When you get up to the higher ones like gold and platinum, they don't corrode, or corrode very, very slowly. So here are the potentials when we're talking about soil. And when you see a minus sign next to this millivolt, or MV, that's a millivolt, that's actually the energy that's leaving the pipe. So that's the energy that's the pipe is getting taken out of it. Remember what I said at the beginning of the presentation, we're actually adding energy when we make it. So this is the energy that's getting taken out of the pipe. And ductile iron will start to give up its structure at about minus 525. That's where we know it'll start giving up. To give you an idea how small of a number we're talking about, this little battery is 3 volts. We're talking about millivolts. So we're talking about not even a volt. This is where we get into some of the science stuff here more. These are the 4 things we need. And believe it or not, when we talk about corrosion, when I talk about corrosion, I try to make it clear that the idea that you're going to get from a lot of different manufacturers of different materials is that corrosion is very simple. You put pipe in the ground and it corrodes and it's gone. And that's not the truth. Corrosion is actually more complicated, and the protection of the material is actually much more simple than that, whereas they want to tell you the exact opposite. So we need 4 things for corrosion to occur. We need a cathode, we need an anode, we need a return current path, and we need the electrolyte. We need a soil electrolyte. We need a corrosive environment for that to occur. So what we do in the ductile iron industry is we take one of those things out of the equation. And once we take one thing out of the equation, we don't have corrosion. It is really that simple. We just take one thing away. So in this case, I'm taking the pipe out of the equation. How am I doing that? We're going to find out. But let me try to put it a more fun way, or a way that maybe we can understand now that the NFL season has started. So let's talk about football. We need 4 things for a football game to play. We need 2 teams. We need the losing team, we need the winning team, we need an electrolyte, we need something for them to play with, so let's say it's the ball, and we need a place for them to play. We need basically the soil. We need a place for them to play, or we need the return current path. So if I take one of those things out, can we play? So if I take the field out of play, we can't play anymore. There's no field, they're just playing on air. There's nothing for them to play on. That's the same thing when we're talking about corrosion. A lot of times when I say energy, they think that this is what's happening when we're talking about corrosion. They think that it's the electric bolt hitting the soil and that's what's damaging that. When that's not the truth. Actually, what's happening is taking it out of the pipe. So we call it de-energizing, some call it decycling, but that's what's happening here. So pulling energy out, here's an example of what a pipe looks like when it's not quite has a hole in it, but it's the energy's coming out of it. You can see it there. And what's happening here is the corrosion, it's called graphitization, and it kind of looks like a piece of apple crumble. It's not quite all the way through on this pipe yet, but that's what's happening. The energy is coming out of the pipe, and what's happening is that energy is jumping off the pipe and going somewhere else. That's what we call stray currents. And if you have like a railroad track or electric current going near it, or the soil is corrosive in that manner, that's what's happening. It's jumping off the pipe and going somewhere else. And when it jumps off the pipe, it takes some of the pipe with it. That's what corrosion is. So what do we do to protect it? Well, there's lots of different ways to protect it. We use cathodic protection, zinc coating, polyethylene encasement, which I'm going to get into a lot, bonded coatings and denso tape. But let's look at a couple of these other ones that are out there and that you're probably familiar with because they've been around and they're used for other things. They're used for the oil and gas industry, which is very important. So let's talk about cathodic protection. Okay, what happens with cathodic protection for those of you that think you may know or maybe you don't know? What it is it's using a sacrificial anode. And we're actually redirecting that energy to go to that sacrificial anode. We're changing the path of that corrosion. When we're talking about impressed current, we're actually even adding something to that. We're adding a monitoring system to it. So we're adding the voltmeter, and we're adding a connection to the pipe and the electrode that's monitoring the soil. So what does this mean? It means permanent maintenance. But does it work? Absolutely. It works very, very well, but you have to maintain it. And it can't just be added and then left. That's not how it works. So how do we know that it works really well? Well, remember we talked about millivolts? Well, if you have a path that this electrolyte or these electrodes are going on, think of this as like a little bit of a sprinkler of energy that's going from path to path, and it'll leave at the lowest one. It'll leave at -525 or for ductile. So what do? Well, we redirect that path. We change the direction. What are we doing when we're doing impressed current? Well, we're basically putting a waterfall of energy on that pipe, and we're changing the current. So we're making the pipe the winner on the field, and the anode the loser, and the anode will be eaten by the corrosion instead of the pipe. What does that mean for the life of the pipe? Well, that means that the anode will have to be replaced probably about 3 times in the span of 100 years. So it has to be maintained. If you don't maintain it, then the pipe gets to be the loser on the field. Some say that zinc pipe is the answer. It's very popular in Europe. But zinc, as we know from that other chart that I showed you, that zinc is basically a sacrificial anode as well. So once the zinc is gone and eaten up on the pipe, then it'll start attacking the pipe. So it's a really good backup system. And this is kind of comes from McWane, and McWane and Canada Pipe are the same. McWane is the manufacturer. And basically what they say is that zinc is an enhancement to protecting ductile iron pipe from corrosion, but it is not standalone. We need something else to be added to that. So I've got a better way. And my better way is polyethylene encasement. And it will take the pipe out of the equation. So just some background information, it was researched in '52. It was first used in 1958, and then it became a standard for AWWA in the early '70s. Here's a case study. So this is how we know what we're talking about, and we know how impactful polyethylene encasement is. This is only 25 years, so we actually still had the same contractor around when we had to dig up this pipe, and this is only 25 years in Cape Cod. This is only after 25 years. This is how corrosive that soil was without protection. So that's how fast it was gone. This is the same pipe 100 feet away. So what are we talking about? What does that mean? I mean, what are we doing? Well, what happened was the contractor that put in the pipe, they ran out of poly and they didn't finish the 100 feet of the line. So it ate away 100 feet down the line, and this pipe here was completely fine. And it still has the stencil paint on it from the factory. This is them digging around to check for holes. This is one of our engineers in the white hat that works for McWane. And that's not just water that he's standing in, that's the ocean. So this is right on the ocean. It's literally feet away from the ocean where this pipe was put. So this is a very corrosive area, and that's why they put the poly, but 100 feet away, it corroded. You can see it again there, 25 years with polywrap. It's basically in water. This is the first one that we ever installed with poly. This is done in the most corrosive soil in North America. It's in Lafourche Parish, Louisiana. And it's a very small pipe. It's only 4 inches, but it was the first one that we ever tried in the 1950s, and or DIPRA tried in the 1950s. And this soil is so corrosive that if you stood in it with your rubber-soled shoes, it'll start eating away your shoes within an hour. It's that corrosive. So when we put the pipe in, we wrapped it in the poly, we took the pipe out of the equation, and now we check it every 13 years. And here's the last pictures that we took of it when we dug it up. So you can see the poly that's on it, then you can see us taking off the poly, and that oxidation that we talked about, that's not rust, that's oxidation. And so we just scrubbed it away with the wire brush, and it's a brand new pipe. And that pipe's been in there since the 1950s. Some local pictures. This is the city of Port Moody that just started using polyethylene encasement on their pipes. And a lot of places ask, including the city of Port Moody, asked me, well, they wanted to come and they wanted me to show them how to install it. So I came and showed them how to install it. And then the city guys were there and they wanted to say, well, how durable is this stuff? How much do we have to worry about it? Well, I took a video, and this is the video. So hopefully it'll just press play on there, and you'll see that they're just dumping it on there. So bottom line is it's very durable. And if you ever want to see, or if you want me to show you how to install it, I'm always available to do that. But here's the DIPRA numbers for corrosive soil. So this is what we know from their own testing. We know that if we sandblast the pipe completely bare, it'll last 10 years in hot soil, it'll be gone. If we do it just regular bare that it comes out of the factory, it's about 7 years more. If we do shop coating on it, maybe 25, like you saw in Cape Cod there. And if we polyethylene encase it, half a millennia, we don't really know. We know that the pipe will last 300 years minimum. If we polyethylene encase it, it could last 500 years. So how do we decide what we're going to do when we're talking about corrosion? Well, we use something called the Design Decision Model, or the DDM. And this has come out recently. It actually uses a likelihood and a consequence factor. And when we're talking about likelihood and consequences, you can see the red line there. That's where we would recommend using cathodic protection. And how do we come up to those conclusions? Well, we use likelihood and consequences. So the likelihood is the soil. Is the soil corrosive? Resistivity, pH, redox, sulfide, moisture content. Curiously enough, when we're talking about water, water is only 2 points on a corrosion scale. You need soil. You need soil. I'm going to repeat it again. You need soil for pipe to corrode. Pipe does not corrode just in water, and pipe does not corrode in air. You need soil. What are the consequences? Well, what's the size of the pipe? Is it large? Where's the location? Is it in a residential area? Depth of cover? Is there any other water supply? If there isn't, and it's a large pipe, maybe we include cathodic protection just as a backup system. The benefits of poly, I don't have to go through the whole list, but the biggest one is on the bottom. No maintenance. There is no maintenance when you're talking about poly. There is no replacement. It'll last the length of the pipe. You wrap it, bury it, and walk away for 100 years. That's it. The new version, basically it's the dummy-proof version that we're selling now, is V-Bio, and what that does is it's a corrosion inhibitor that's built into the plastic. And what it'll do is it'll stop all corrosion, including that oxidation that you see, that browning of the pipe. It'll stop that as well. And how does it do that? Well, this is what it's made out of. It's made out of low-density polyethylene. It's co-extruded. There's a food-grade biocide that's put in it, and that's very, very safe because you probably use it every morning. It's the same ingredient that's in your toothpaste. So that's what that is. For some scientific proof of it, these are corrosion probes that are put underneath polywrap. This is regular polywrap, and you can see the different bumps on there. That's eating away the oxygen that's still left underneath the bag. So that's what that is. That's why you'll get some of that oxidation under polywrap, because it's eating away the oxygen. You need oxygen to create oxidation. And this is V-Bio. So there's literally nothing, because it'll kill it all. And I had a corrosion engineer look at this, and he said, well, I don't really like the V-Bio stuff. And I asked him, why don't you like it? And he said, well, I don't get any readings on my equipment. And I said, well, isn't that kind of the point? We don't really want any readings at all. So bottom line with corrosion, the industry is iron. We have to figure out and face better ways to protect that, because all these things are included. You can wrap all of these things with polyethylene encasement, all of that stuff. And nobody is immune to corrosion. As much as other materials will tell you that they're corrosion resistant or they won't corrode, nobody's immune, because of situations like this, for example. The fittings are not protected. The corrosion doesn't know the difference between a pipe and a fitting. It's going to eat whatever it's going to eat. Here's an example. This pipe was put in 20 years ago. That's what they told me in this community. I won't name the community, but that's what they told me. And I said, what was your corrosion plan? And they said, our corrosion plan was using PVC pipe. Well, you can see that the fittings didn't last. The pipe looks great, but without the fittings, you don't have a pipeline. So putting corrosion aside, let's get into some environmental aspects of ductile iron pipe. Let's get into fluid dynamics. Let's get into hydraulics. And that's really, really important when you're designing a pipeline. So economics and longevity of pipe, we need durability, longevity, efficiency, operating cost, maintenance cost. All those are included, and including pumping costs as well. So what affects your pumping costs? Well, what's the length of the pipeline, obviously, the water velocity, how much water is going through it, the C factor, which is something that the other pipe materials like HDPE and PVC, they really talk about that because they have a good C factor. So they talk about that a lot, and that is a variable. Internal diameter is the biggest variable that you're going to get in a pipeline. The size of the inside of the pipe is what determines pumping costs mostly. So we're going to talk about water infrastructure and economics. Here is the different aspects. So this one is HDPE, internal diameters, based on, this is based on a 14-inch pipe. This is PVC, so it's bigger than HDPE, you're letting more water through. This is steel, and this is ductile. So you're getting a lot more. In fact, you're getting about 38% more water through. Here's HDPE. It's got some pretty thick walls, and it can handle a lot of high pressures, which is great. It's got a good C factor, which is good, but you can see how thick the wall is. Here's an example of what the equivalent for ductile would be for the same pipe. And it's a really, really thin wall comparative, so it's a lot larger of a wall. If you like numbers, if you're not a visual person and you like numbers, these are the numbers. I can always send them to you if you want to give me your contact information, or they're in AWWA if you want to look at them. But it really starts to make a difference when you're talking about getting up to 12-inch. You're getting a lot more. Anytime you get past 8-inch, you're getting a massive amount of difference when you're talking about internal diameter. So we're going to get into why that's important. So on average, 38% of the energy used by municipalities is consumed by water and wastewater systems. So what does that mean exactly? Well, it means that they're the biggest customer of the electricity. They're pumping the most water, and they're using the most energy to pump that water. So if we can increase the size of the diameter of the pipe, we can pump more water through and use less energy. That's really important when you're talking about it. So we obviously want to decrease our carbon footprint. This is one good way to do that. And ductile iron pipe, like we've already gone through, it's obviously safe. It's made from recycled materials. It's energy efficient, and it has a 100-year life cycle. There it is again. This is from the University of Michigan. They did a study on water materials. If you want to see this, you're more than welcome to. You can look it up. It's free. I can send it to you if you want. But this is their flow chart, their life cycle flow chart that they came from: recycled content, energy going in, greenhouse gases that are coming off, and end of life. So this is a cradle to grave cost, and that's what we have to look at when we're talking about infrastructure. This is how the University of Michigan is given life cycle in years, DI versus PVC. AWWA gave PVC less than probably they deserve. They probably deserve a little bit higher than that. And some of them will give about 60 to 70 years, and they'll give ductile about 100 to 120 years on a usable life cycle. This is the CO2 emissions that are put out, and we have to realize that this CO2 emissions are not just pumping costs, they're actually manufacturing costs as well. So remember, we're talking cradle to grave life cycle here. So this is, when you're talking about the bigger the diameter you get, the more pumping costs will incur when you use a material that has a smaller diameter. So we also have to talk about head loss, and that's what they talk about. They always talk about C factor and a smooth pipe. That's what a C factor is. It's the Hazen-Williams factor, and this is the head loss formula. I'm not big on the math side, but if you ever want it, you can have it. I'll try to break it down a little bit more clearly for you. And we're going to do that with a case study in a second here. But C factor. So ductile iron pipe, we'd use cement mortar lining. We have a C factor of about 140. PVC uses about 150, and we know that ours stays at 140 to 135. It doesn't go below that, and we know that because we've been installing cement mortar lining for about 90 years. So we have a lot of material to look at and determine that that's the truth. Velocity of water flow is really important. When we're depending on pipes, the velocity of water will vary, but the demand for the flow rate will always stay the same, or it'll increase. It'll always increase or stay the same. It'll never, ever get lower. So knowing that ductile iron pipes have a bigger inside diameter results in lower velocity compared to other materials. in the velocity is lower, the head loss will result in a smaller value, and that's lowering your pumping cost and your energy consumption. Let's talk about fluid dynamics. What you'll hear from different materials is you'll hear that C factor is really important because it has a rough, and if it goes smoothly on the sides of the pipe, then you're going to get better flow, and it's going to be better for fluid dynamics. But that's not how water flows. Water doesn't flow flat. Water flows on a laminar flow. So what does that mean when you're talking about an inside of a pipe? Well, the lowest velocity is on the edges of the pipe, and the highest velocity is in the middle. So if you have a bigger diameter, you're getting more water through because the most of the water is flowing through the middle and not through the sides, because it flows on a laminar flow, a bubble like this. This is basically a quote from that University of Michigan study. When laminar flow exists, the fluid seems to flow as several layers on top of the other because of the viscosity of the fluid. A shear stress is created between the layers of the fluid. Energy is lost from the fluid by the action of overcoming the frictional force produced by the shear wall stress, not because of the friction of the pipe wall. So the pipe wall doesn't have any real effect on how much water is being pumped through that pipe. So here's a case study if you want to see when we're talking about money here. So when I talk to cities and municipalities that use a lot of PVC and HDPE, we can talk to them about environmental, and a lot of them that's important to them. But what really impacts them is money, and for good reason. So we're basing this on only 1,000 meters. It's a 14-inch pipe. Here's the pipe that they have the ground. They asked me to come in and do it after the fact, so they had already installed the PVC, but I took a picture of it because I thought it was interesting. So this is the pipe that they had on the ground at the time. You can see the wall thickness. Here's the ductile pipe. That's the difference between the two. So you can see that internal diameter is a lot bigger. So let's look at this as their practice. This is the numbers that they gave me, by the way. So this is what they work on. It's probably changed now, but 13 kilowatts per hour. It might be higher now. 70% efficiency at pumping 24 hours a day. The design life that they wanted was 100 years, and the rate of return 5%, inflation cost 2%. Some city at Delta facts is that 700 liters a day per person per day. That's what we're basing this on. 50% of the water that they use is actually for lawn and gardening. So half the water they're just spraying out onto the lawn. And they have 608 kilometers of water main in a small community like this. So this is the one DIP versus PVC on that Byrne Road project. So you're looking at this and you're probably thinking, Brent, it's not a big deal. We're talking about at the bottom line of pumping cost, annual pumping costs, we're talking about $13,000 compared to PVC, which is $16,000. That's not a lot. Let me show you something. Cost of savings per year, present value. Remember that they have 608 kilometers of water main. We're talking about 1,000 meters. We're talking about 1 kilometer. So what does that mean when we're adding it up? Well, this is their scenario. They have mostly 8 and 14-inch pipe. Their 8-inch pipe, present value, $38,000, about $1,000 per kilometer. 14-inch is that, $102,000. And when we add 608 kilometers of water main in their system, that will equate to about $582,000 on 8-inch and about $388,900 on 14-inch. Well, if we give the city, if we switch them to ductile, they'll save per year almost $1 million a year just on pumping water. And that's in a small community. So bigger communities, saving millions and millions of dollars. So putting hydraulics aside, we're switching again. We're going into durability and we're going into seismic concerns. And seismic is a big hot topic in the Lower Mainland here. The city of Surrey and the city of Vancouver are rushing to put in seismic lines now. And this is what they're doing. This is why they're doing it. They're putting in seismic lines for these different factors: liquefaction, permanent ground deformation, surface cracks, ground subsidence, and anything that's soft or disturbed earth. That's really important to have a pipe that's going to be, or water delivery system that's going to be able to handle those changes in the soil. So this small area here, and I'm sorry for everybody that's out of province, but when we're talking about the seismic concerns, we're talking about the Lower Mainland in British Columbia. 3.7 million people live in this small square, and only 2 of them have a seismic plan right now. None of them are on the island. And that's the one that we probably should be worrying about the most. So I'm working hard to talk to them about it. But what is liquefaction? When I said liquefaction, what does that mean, and why does it affect pipes so importantly? Well, here's an example of what liquefaction actually is. That's what happens when the ground is not able to stay structural integrity. It's not going to be able to, it'll shake and it'll basically turn to quicksand and swallow anything. So we know, anybody that's an operator out there will know that if they install PVC pipe, they need, what do they need? Backfill. They need pressure against the pipe to hold on to that pipe. They need pressure against the pipe to keep it structurally sound so it can pump water. What happens if that trench is gone, like in this situation right here? What happens? It's gone. The pipe is gone. There is no pipe anymore when you're talking about this kind of effect. So you need a pipe that's going to be able to handle being able to pump water without having to worry about the trench, if there is no trench. So what we ask for in a pipe, and what we've come to talk about when we're selling seismic solutions, is we talk about ruggedness, resistance to bending, joint flexibility, and joint restraint. Well, if you've ever seen what's out there, is they'll actually tell you the exact opposite. They're actually saying, oh, we want a flexible pipe and we want a stiff joint because they have to restrain the joint, but we're telling you the exact opposite. I'm going to try to prove why that's important. These are the different pipe-soil interactions that we worry about when we're talking about seismic considerations. We talk about a slip strike differential, that's the most violent one, and the other ones where the trench will basically be gone, different crossings that you have to worry about. This is actually a piece of ductile iron pipe that's in Japan. And this is what happened after the earthquake. And you can see, I'll give you a better example when I show you the short little video, but this is a sinkhole that happened after the earthquake, and there's only one pipe left standing, and that's that small one on the right-hand side. It's actually a 12-inch pipe, but it's still pumping water right now. So hopefully this will play, but this is the actual video of that same sinkhole. And you'll see the pipe bounce. You can see it on the left there, on the right there. It's swinging and bouncing. That's a piece of heavy 12-inch piece of ductile pipe that's just swinging and holding itself together. That's TR flex pipe. So that's how we know there's an example of it. Just move on, you don't see the whole thing, but that's the same sinkhole. Want to just skip ahead for me there? There we go. So when we talked about liquefaction and trench problems, well, this is what happens when you're talking about external loads on the two other guys. So that's what we have to worry about when we're talking about earthquakes. This is steel pipe, and this is a compression of steel pipe when it's in an earthquake. This was actually done in California, and the steel pipe actually just crushed under the weight. And this is the chain effect that we talk about. So when we talk about joint flexibility on a piece of ductile iron pipe, for example, this is how we know, and this is how we know that it'll work and it'll stay together in a seismic event. And I put something together for you so you can see when we're talking about chain effect, I actually used a real chain. So this is, let's pretend all the links on this chain that you're going to see are the joints. So here's an example. This just needs to press play on it. So this is a regular pipe where there's no joint flexibility, and let's pretend A is a hydrant and B is a fitting. So when there's ground deformation, you're getting it pulled away from the hydrant and the fitting, and you have a leak. The pipe may be together, but what it's attached to is not. So now we're putting it on a chain effect pipe, which is a joint flexibility pipe, and let's watch what happens when we pull the chain. So everything stays together. So that's how that works. So McWane has come out with even more to go on to the TR Flex. We call it the Seismic Flex coupling, and it's out of design now, and it's gone into manufacturing. So we're trying to build as much inventory as we can now, but we're still getting it to market. So, but this is an example of how of what it's going to be and how it's going to help seismic communities. So it's a Seismic Flex coupling. It's Cornell University tested. We can do new installations, and we actually can do retrofit installations, which is really important because there's a lot of other ductile companies out there that will do a seismic line, and they have to be a new line. So it has to be a new construction. We can actually do both. It all matches the ISO standard, which is 16134. It's an international standard for ductile iron pipes, ductile iron earthquake resistant pipes. And you can see this is the example of how it will work on a 4 to 12, fully compressed, mid position, fully extended. It'll give about 11.5 degrees of deflection on a pipeline. And this is between SFC, or Seismic Flex coupling, and TR Extreme, which is the US pipe version. And the US pipe one is actually in the market now, and they work very, very well. But the SFC will just add a little bit more. This is the ISO standard. This is what it actually is, and we fall in S1, B, and M2, which is pretty high when you're talking about a seismic pipeline. If you want to know information about that, please feel free to send me an email. I'll be more than happy to walk you through all that stuff. I know this is kind of quick, and I'll be more than happy to walk you through all that. To give you an idea of how it compares, when we're talking about a seismic flex coupling, that doesn't mean that we have to put it on every joint. If we did put it on every joint and we had 1,000 meters of a pipeline, it'll move 2%, basically. So it'll move 20 feet, basically, or 20 meters, excuse me. And if we had one on every other joint, it'll move 1.1%. If we had it on every third, it'll move 0.75%. So it'll still move about the same as the TR Extreme does. So that's where it's equal to on every third joint. Expansion, contraction, and all that. When you're talking about a joint deflection angle, for the tighter the number, the tighter the radius of curvature, the smaller the number, the better it is. And when you have a radius of curvature of about, when you have it on every joint, you have a 97 or 125, or every third you have 142, whereas the TR Extreme is about 255. And TR Extreme is actually in working order now, so it's a very good product. It does work. We're just trying to add to it. Here's another offset of the different ductile iron manufacturers: US Pipe, American, Kubota. Kubota is Japanese, and they're actually in the market as well. They did a job in Vancouver as well, and their deflection is about 6 to 8. Ours is about 11, so we're pretty equal. We wanted to be able to move as much as we needed to. This is what I was talking about when I was talking about retrofit applications. This is basically a gripper ring. When you cut the pipe and you put this gripper ring in, you can change it to TR Flex, and then you can go on with your Seismic Flex coupling. So that is available if we need to do retrofit. And last slide will show you how the Seismic Flex coupling works. So go ahead and press play there, and I'll let you see that. I'll kind of walk you through it. There's no sound on it. So the Seismic Flex coupling will come assembled already. This is just showing you how it does get assembled, but there's 2 pieces involved in it. It already is assembled when it comes. It'll actually be red and blue. So this is also too how TR Flex is, like you saw in the first video with the TR Flex pipe. It just 2 locking segments are in there, depending on what the size of the pipe is. And it's the regular TR Flex, the black on either side. So when it's pushed in, You'll be able to handle expansion and contraction, and then fully extended as well. It's about 10.5 inches. And then you get 5 degrees deflection, you get 1.5, and then you get 5 degrees deflection on the other end, so 11.5. And they're going to show you quickly here on how it would react on every other joint in a situation. And keep your eye on the hydrant on the left-hand side. We don't want it to move at all. So you have a big movement and a drop in the ground, and that's how the pipe will hold together. Again, my name is Brent Williamson. Thanks so much for inviting me and listening. I'd love to talk to all of you if you have questions for me. I love questions. As a sales rep, they are the best. If you provide your emails when you ask your question, I have a prize for you all. If you provide your emails and your contact information, I have 2 tickets to an upcoming Vancouver Canucks game, and you're more than welcome to them. I'll draw from the names, and I'll let you know who wins, but I would love to have questions and to follow up with all of you. Again, thanks so much. I'm here.
I have a couple questions.
Sure.
Thanks for your presentation.
No problem.
That was great. So one of the questions that came up on the chat was wondering if anyone has ever experienced any changes in pH of the water in ductile mains with low flows. And then the second question they entered was possibly from the breakdown of concrete lining, question mark.
No, that's not to my knowledge that hasn't happened, because the concrete lining won't break down. We have different studies, and I can get those to whoever asked that question. If you want to see the studies of how the cement mortar lining holds up, I can get those to you, but it holds up for the length of the pipe, so 100 years. It doesn't break down over the time, so you won't get any pH change.
Okay. And then the other question was also related to cement mortar lining. Is the cement mortar lining equally as flexible as the DI pipe?
Yes, and it is. And the reason why it is because we put it, as you saw on that picture, they spray it in. And when they spray it, you only need a very, very thin amount. So when you spray it in and it's able to flex and move, it'll move with it because it's basically almost like painted on. So it's very flexible. If it's double cement lined, in some cases you may get some chipping involved, but you still need, to get any kind of internal corrosion, you need something for that iron oxides to attach to. So if there's not enough iron for it to attach to, it's not going to change anything on the water.
Okay. And I did include a link to the McWane website
Oh,
that
great.
talked about the lining. I'll
Yes.
put that right into the chat.
I have 2 more questions.
Sure.
Okay.
One is, would these work in Gold River, west coast of Vancouver Island?
What was that, sorry?
Would these work in Gold River, the west coast of Vancouver Island?
Absolutely. Yeah, we're starting to put them more into the island now. The CRD, which is the Central Regional District for the island, only uses ductile iron pipe. We've sold to them for years. So.
Okay, and just one more question. Does the hydrant have that coupling as well?
You don't. It didn't have it on that scenario, but that's actually a really good question, because what's been going for that coupling is they've been asking for it for going inside of buildings or being attached to a hydrant and only to the hydrant, so it'll move with that, and then they're going on with the rest of their pipeline. There's lots of different engineering factors that are going into it, but that's a great question because that's a really good application for it. And going into buildings, they're starting to use it in downtown Vancouver. They want to use it. We're trying to get them some bigger sizes that we're making, but that's their idea, is to put it into going into buildings to make them seismic ready, basically.
Another question we have. Are sales starting to tip in favor from plastic?
Well, we always have a very good market here. There's always going to be plastic. I mean, even if I got rid of all the plastic in BC, I wouldn't be able to supply all the pipe. Even there just wouldn't be. So there's always going to be room for plastic, and but this is the biggest ductile market in Canada. It's a over $10 million a year market. So.
Okay. Next question was, can these products be used with ozonation?
I'd have to look that one up. I'm not familiar with ozonation. So if you give me your contact information, I'll look it up for you.
It's right there. I got it.
Oh, you got it. Good.
Yep.
Yeah. I'll look
Okay.
it up for you. Absolutely.
Any
Get you
more
that.
questions that you see there, Kim?
Sure.
How does the cost of a length of ductile and poly bag compare to, say, C900?
Yep.
Mm-hmm. Yep. So it depends on the size. That's the biggest factor. So if you're talking about a 6/8, the PVC is going to be substantially less expensive on those sizes. Once we get up to 10, 12, 14, 16, the ductile is actually less, especially with the increases that PVC's had in some places, not in this location, not in Vancouver, but in some locations in Canada, they've gone upwards of 40%. Because of the problems with manufacturing and getting resin because they get it all from Texas. So when Texas has those environmental problems, the freezing, and then they had hurricanes, their cost goes up. So if it depends on the size. If you're talking about 6 and 8, it's going to be less. But then that's why we talk about pumping costs and we talk about installation costs and all those kind of things come into factors as well.
And then, actually, another one, some more that have come in. One, great presentation. Where on the island can it be purchased?
All the distributors have it. So the Iconics Waterworks, Wolseley, Andrew Sherritt, all those distributors carry Canada Pipe.
What is the most bought on the pipes, as in sizes?
Oh, that's a great question. Our bread and butter sizes are always going to be 8, 10, 12, 14. We sell a lot of 6-inch as well. It depends on what they're doing with it. If they want to have 6-inch and they're choosing to use that instead of another material, they're probably using it because it's high pressure. They need to worry about high pressures, and we can handle more high pressures. But yeah, the bread and butter sizes are always going to be 8, 10, 12, 14. And then once we get bigger, when we get to 24, there really isn't any competition that in this area anyway. We put in all of the larger sizes. The City of Vancouver put in 36-inch pipe all the way down Powell Street here. So.
Just a lot of impressive products, and thank you. And
Oh,
excellent presentation.
thank you, everyone. Thank you. I'm available.
Thank you.
Awesome.
So we'll reconvene in the water stream at 3 o'clock for the next presentation. So you're welcome to join the other streams currently. Thank you.
Thanks, everyone.